Hello everyone and welcome to another episode here of the Hidden Quantum Champions on the Polaris School of Quantum YouTube channel. In today's video we are going to check out single quantum, and without further ado, let's grab something to drink and then get right into it. So here we are on the website of the company Single Quantum. It says Single Quantum Excellence in Photon Detection, and then Single Photon Detection. Single quantum makes the world's fastest and most sensitive light sensors, limited only by the laws of physics. So now you could of course ask the question, why are light sensors now relevant to the topic of quantum technology? And I hope that we can answer that by scrolling down, but for sure there will be some information. So here it says, what's new with single quantum? So here we are, I guess, in the news section with the latest products announcement. That says Single Quantum and QNECT partner with CERN QTI on quantum networking experiments at newly inaugurated Quantum Lab. And then there's some product announcements here about the Single Quantum EOS coming soon and the integrated vacuum pump available now. So there is like product announcements here introducing Single Quantum Germany, our new office, so company news, and then of course things like this, which already give a hint on the fact that this company is playing a role in the quantum technology ecosystem. So let's scroll down a little further, and we see in the solutions and technology part here one of the products. So you see it sits in this black rack type of shape. This is the product I think that we've seen earlier before. And this is the full system, so it's called the SNSPD. Discover our SNSPD product lines. Single quantum multi-channel SNSPD system can detect single photons with over 90% efficiency and ultra-high timing resolution for less than 15 picoseconds. So just as a quick reminder, so there is milliseconds, 10 to the minus 3, microseconds to the minus 6. Then you come to the nanoseconds, then the femtoseconds, and then the picoseconds. So was it femto, pico, or pico, femto? Well, it's a very short time. That's something that I can say, and everything else you can anyways look up. And then here it says, so, I mean, this is quickly to wrap this up. So this is a single photon detector with a very high efficiency. And this statement here about being only limited by the laws of physics, we will learn more about that in a second, I think, when we are looking into what SNSPD actually means and what it is. Then there's some more information here about learn more about how it works. So that's what we will see, how the technology works. Then I guess here we have some testimonials, for example, from the University of Stuttgart, from the University of Vienna. So it's all very European ones, and the University of Rochester. And just as one example, from the University of Stuttgart, Dr. Simone Portaluppi says, working with single quantum systems has a big advantage. Not only you operate with a state-of-the-art device, very much user-friendly, but you can count on the persistent support of a team of highly trained professionals. And then down here you find some more information, cutting-edge scientific research around the globe. So I guess there you find probably some projects that they are part of, maybe some collaborations, and possibly also some publications that they are part of. Then it says innovation quality service, more about us as a sincere company with a straightforward vision. Single Quantum is developing the world's fastest and most sensitive light sensors, limited only by the laws of physics. And then harness the power of SNSPDs. With that, let's quickly check out exactly this technology. So the operation principle of the SNSPD, which so the technology behind single quantum solutions is the SNSPD, which is superconducting nanowire single photon detectors. So here you see an image of what the process looks like. So you have this meander type of superconducting wire. So it's a very thin strip of superconductor. I guess it is being produced using lithography processes. So you can make this micrometer or nanometer thin lines at a very narrow spacing, and you can even, because it's usually evaporated, you can assume that this is only nanometers to micrometers thick in height as well. Now you have this wire and you can apply a current to it. And because it's a superconductor, if it's stored at a cryogenic temperature, this will not produce any resistance. So the wire will be superconducting up until you reach the critical current. Then, of course, the superconductivity will break down, and then you have a normal resistor. So you will measure that there's a voltage drop across the system. So you can measure with a voltage probe if the wire itself is superconducting or not. Now, that said, you can now assume that if you apply a bias current, which is very, very close to the critical current, then every small little perturbation to the system can already trigger this transition, this phase transition, where your wire goes from the superconducting state to the normal conducting state. And the absorption of a photon is exactly that. So if a light particle, a photon, is hitting this structure here, this meander structure, the metal, it will be absorbed because metals absorb photonic interactions, right? Metals are conductors and the photon is an electromagnetic wave. So it's getting absorbed in here. And when doing so, it creates a heat. So there's like heat dissipation happening. And by this heat dissipation, of course, that means that your superconducting area here is breaking down because you are already at the critical current. So as soon as this heat is being dissipated in this specific area, in this very narrow place here, the superconductivity is breaking down. But as the heat is spreading within your system, and that happens within a very short amount of time, you saw the time to measure this photon here is actually 15 picoseconds. So this is spreading very fast and thereby breaking down the whole superconductivity, creating this resistive barrier here. So you measure that suddenly there's a voltage drop across your system, and then as the system is cooling down again, so this is this tau2 time here, which it takes for the system to recover. As this is happening, your system is becoming superconductive again. Now quickly in the explanation of the text. So the single quantum multi-channel SN-SPD system combines high detection efficiency, high time resolution, low dark count rate, which is the rate of counts which are actually no counts, so kind of like the noise, I guess, and a high count rate. It can detect single photons with higher than 90% efficiency over a broad spectral range and the ultra-high timing resolution of less than 15 picoseconds. The SN-SPD consists of a thin film of superconducting material shaped into a meandering nanowire, maximizing surface area to collect the full output of an optical fiber while maintaining a single current path. Operated at 2.5 Kelvin, so quick note here, liquid helium is at a temperature of 4 Kelvin, but if you actually reduce the pressure of a liquid helium vessel, so if you have the liquid helium and you reduce the pressure, you also reduce the vapor pressure by that, and that means your helium is boiling off and you are left with a colder liquid helium stage. So that can go up to down to I think around 1.4 Kelvin. So this can still be achieved with a normal liquid helium cryostat technology. So back to the text, operated at 2.5 Kelvin, a constant current below the superconductor's critical threshold is applied, and its nanoscale cross-section enables high density of single photons. When a photon is absorbed, superconductivity is locally disrupted, redirecting the current to amplification electronics and generating a voltage pulse. With tens of nanoseconds, the wire recovers its superconductivity, ready to detect the next photon. And that's basically how it works. There's the single pixel technology here, so our single pixel SN-SPD operating with a range of 600 nanometer to 2 micrometer, deliver unparalleled detection efficiency and time resolution, making them ideal for quantum communication, cryptography, infrared fluorescence spectroscopy, laser ranging, and more. For the multi-pixel SN-SPD, it says single quantum developed multi-pixel detectors based on interleaved nanowires with all the pixels running independently. Multi-pixel SNSPD systems can be used for imaging as well as for photon number resolving or ultra-fast single photon detection. And then there's other detector technologies like the photon number resolving, so PNR detectors, have the ability to distinguish the number of arriving photons. The multi-pixel approach with interleaved detectors is based on the parallel landing and readout of photons onto a detector array whose pixels are uniformly illuminated. With 4 pixels, you can simultaneously detect up to 4 photons at the same time. Then the high count rate detectors, single quantum developed multi-pixel detectors, can based on interleaved nanowires with all the pixels running independently. Because of their multi-pixel nature, the interleaved detector are much faster. Each pixel can reach full efficiency recovery after only 4 nanoseconds at 1550 nanometers, which is the wavelength, right? We've talked about that in earlier videos as well. And then quickly on the gated SNSPD. So Single Quantum has developed a fast gated SNSPD that allows full efficiency restoration in less than 5 nanoseconds with a gate window of 20 nanoseconds. The perfect choice for cutting edge experiments which require rapid temporal filtering with flexible photon detection window. And then there's some information here on the different cryogenic solutions that they have. Like for example the EOS, which is the flagship product, but there's also other ones like for example this AtoCube helium compressor here. AtoCube IGLU, so igloo, is the newest product added to the fleet of helium compressors you can choose from. It is compatible with single quantum EOS, EOS R12 and IRIS-X, and combined with EOS R12, igloo provides the most compact rack-mountable solution on the market. So that's what we saw before, right? This is the cryogenic compressor down here. And then you have on top these 2 rack mounts here, which are the single photon detector systems. Then there's another one here, the Sumitomo, the new 19-inch rack mountable compressor from Sumitomo is now available. It is 9U, which is the rack size. The CNA11RC is compatible with single quantum EOS, EOS R12 and IRIS-X. There's also information here about optical couplings and accessories, but I'm not going to go into the detail of those now. Then quick words here on the fastest detector on the market, which is their statement, right? Only limited by the laws of physics. So the time resolution of single photon detectors is characterized by the full width at half maximum, FWHM, which is here from the peak, of the variation in the temporal delay from the absorption of a photon to the generation of an output electrical pulse, which is defined as the time jitter. Single quantum SNSPDs have demonstrated the lowest timing jitter on the market, achieving thanks to the cryogenics amplification. A cryogenic amplifier encased and mounted to the 40K stage, so 40 Kelvin, of the cryostat enables the SNSPD to reach the highest signal to noise ratio and thus the optimal timing jitter. A typical single quantum SNSPD with a cryogenic amplifier reaches less than 15 picoseconds timing jitter. And that's basically what you can see here. So you see the time is here noted in picoseconds. You see the peak here, which is a normalized photon counts peak. And what you can see, so timing jitter at 900 nanometers, I guess, is the wavelength. And what you can see is the full width half maximum. So basically somewhere here, which is kind of the half of the peak, right? The 0.5 is then 13.42 picoseconds between those, or the width of this peak. That's how it's being measured. Okay, and then there's some more information here. So Single Quantum has been supported by the European Union's Horizon Europe Research and Innovation Program under the following grant agreements. And I think that's the explanation page here. Okay, something else that might be worth also noting, I think I saw it somewhere here. So around this 40K stage, so they're basically using a amplifier. So as explained right in the earlier text, there's the superconductive stage. When the superconducting part is collapsing, then the current that is being kind of the current that is not flowing anymore through the superconducting circuit is creating a voltage drop, which is then being used by the electronics for amplification. And now if you would, for example, send it out of the cryostat all the way to the room temperature setup, then you always have the thermal noise in your transistors, in your amplifiers, and that creates a certain noise ratio. Now, if you take this exact same electronics and put it in cryogenics, it will probably not work. But if you have a special electronics that can operate under cryogenics conditions, usually the performance will be much better. And that's why they actually store these amplification stages here at lower temperatures, because by that you get a better signal to noise ratio in a way, a better electron mobility. And if you then have a high mobility transistor type of setup, then you can probably get these very nice results that they're showing here. Besides that, little quick look at the application area. So where is this actually being used? Our SNSPD. SNSPDs offers unparalleled detection efficiency and time resolution, making them ideal for quantum communication, cryptography, infrared fluorescence, spectroscopy, laser imaging, and more. Experience the future of secure and ultra-fast data transfer, safeguard sensitive information with advanced cryptography, and explore hidden insights in infrared fluorescence spectroscopy. Elevate laser ranging to new levels of precision and revolutionize industries like biomedical research and telecommunications. And then here it goes into the different application areas. So you see the quantum key distribution. This is also something that we've discussed earlier on in this video series. Quantum key distribution plays a key role in the idea of this quantum communication. So this basically eavesdropping safe way of communicating using the laws of quantum mechanics. So here it says one of the most promising approach to ensure a secure communication is quantum key distribution, QKD, a quantum cryptography method to produce and share encryption keys. Moreover, quantum internet can enable sending and receiving quantum bits, qubits, over a large network, paving the way to cloud quantum computing. Here, single photon detection is the key enabling technology. Then space QKD, so space-based quantum key distribution, and you might have heard some news about that also from the Chinese government, saying that they have enabled this already and that they are using this already. So I remember when I was back in China for a conference, actually that was before the pandemic, I was going to Shanghai, and we were taking a little walk around the laboratories there, and indeed I saw exactly these type of detectors there. So they had little cryostats and the glass fibers going in, and then inside of these cryostats they had exactly these SNSPDs, so the meander structures of superconductors. They also showed us the cleanroom facilities where they were producing those. And it was very impressive to see all of this research in this area going on. So here it says space-based quantum key distribution, QKD, enables global secure communication by transmitting quantum states like single photons between satellites and ground stations. In optical ground stations, OGS, SNSPDs are vital for their ultra-low dark counts, reducing detection noise and low timing jitter, ensuring precise photon detection. These features enhance the efficiency and security of quantum key generation, making SNSPDs indispensable for space QKD. Then there's something about the quantum information side of things. So quantum information leverages principles like superposition and entanglement to process, store, and transmit data, forming the foundation of quantum computing and communication. Superconducting nanowire single photon detectors are crucial in these systems due to their high detection efficiency and ability to handle high photon rates, ensuring accurate and reliable measurements of quantum states critical for these technologies. So that's, I guess, regarding photonic quantum computing approaches, right? Then you have this deep space optical communication. So this is probably also about satellites communicating with each other. It says deep space optical communication enables high-speed data transition across vast distances using laser-based systems to gather efficiency, to greater efficiency than traditional radio waves. This technology, tested in the Psyche mission in collaboration with ESA and NASA, showcases its potential to interplanetary data links. Superconducting nanowire single photon detectors are integral to these systems, offering exceptional sensitivity and low noise, ensuring reliable signal reception even over extreme distances. And there's more to come here. So photonic quantum computing, I've already mentioned it before. It says photonic quantum computing relies on manipulating photons to perform quantum operations, offering scalability and room temperature operation advantages. Photon number resolving, so PNR, SNSPCs are crucial in this field, enabling precise measurement of photon states, which is essential to error correction and complex quantum algorithms. And then there's also LiDAR related stuff here, but I'm not going into that for now. Then there are also some experiments that have been making use of this technology. So you see here the European Photonic Quantum Computer, EQUIP. There's also ALQU, algorithms for quantum computer development and hardware-software co-design, advanced cryogenic technologies for innovative computing, and there's more on imaging over here. You can also find application notes down here for these various different applications mentioned. For example, characterization of a quantum entanglement photon pair source, which is what you need for this quantum key distribution, for example, and many, many others. And again, then here you find the testimonials that we've seen before. Good. So with that, let's hop quickly into the About Us part so that we learn also a little bit more about the company itself. It says Innovation Quality Service. As a sincere company with a straightforward mission, Single Quantum is developing the world's fastest and most sensitive light sensors, limited only by the laws of physics. With over 10 years of experience and satisfied customers worldwide, we are the global leader in commercializing SNSPDs. There's also this video here, which we are not going to watch now. Then it goes on to say, at Single Quantum, we confront every challenge with innovation, dedication, and passion. With over 10 years of experience and satisfied customers worldwide, we are the global leader in commercializing SNSPDs. Okay, that's what we've heard already. Founded in 2012, our team emerged as true pioneers of single photon detection technology. We are among the first to manufacture and commercialize superconducting nanowire single photon detectors. Since then, our multi-channel single quantum EOS photon detection system has been chosen by more than 250 academic and industrial labs all over the world to perform complex optical measurements. At the heart of our organization lie our core values, guiding every decision we make and every action we take. So here are the core values. It's respect, trust, proactiveness, teamwork, impactful innovation, and quality. And I'm not going to go into the details of these now, but you can read them on the screen yourself if you're interested. Then we see here the management team, which seems to be very scientific. So we see a lot of PhDs here in the board. And then there's the call to action here to join the team and become part of their of their company. And with that, I would say we are already at the end of today's video. If you liked it, please make sure to give it a thumbs up. And if you don't want to miss out on the next one, then make sure to subscribe to the channel. See you in the next video. Bye bye.